In 1989, 6 million people lost power in 90 seconds. In 2012, we missed a civilization-ending event by just 9 days. And now, as the sun reaches its peak of violence, we have to ask the question that haunts every space weather scientist. When the next great storm comes, will we be ready? Or will everything we have built simply go dark? But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. Right now, as you watch this, something is happening on the surface of our sun. Dark regions the size of Earth itself are rotating into view. Some of them are 10 times larger than our entire planet. They're cooler than the surrounding surface, which is why they appear dark against the blinding brilliance of our star. But do not let that darkness fool you. These sunspots are among the most violent and unpredictable features in our solar system. In the chapters ahead, we will journey from the surface of the sun to the depths of history. We will witness the greatest solar storm ever recorded, and the moment 6 million people lost their electricity in 90 seconds. We will explore the invisible shield protecting all life on Earth and ask the question that haunts scientists around the world. Could the sun, the very source of all life, become the instrument of our destruction? And if that day comes, will we be ready? Chapter 1. The dark spots on our star. The sun appears unchanging, a yellow disk hanging in the sky, constant and reliable. We wake to its light. We set our clocks by its movements. We take for granted that it will rise tomorrow exactly as it rose today. But the sun is not constant. It is a churning ball of superheated plasma, a nuclear furnace, burning through 400 million tons of hydrogen every single second. And on its surface, where temperatures reach 5,500 degrees, there are storms that make the worst hurricanes on Earth look like a gentle breeze. Sunspots have been observed by humans for thousands of years. Ancient Chinese astronomers recorded dark marks on the sun as early as 800 before the Common Era. They believed these marks were omens, signs from heaven that something significant was about to occur. In a way, they were not wrong. Sunspots do signal something significant. They mark regions of intense magnetic activity, and where there is magnetic activity on the sun, there is the potential for explosive violence. The modern scientific study of sunspots began in the early 1600s. Galileo Galilei turned his newly invented telescope toward the sun and saw something that contradicted the religious teachings of his time. The heavens were supposed to be perfect, unchanging, eternal. But there on the face of the sun were dark blemishes that appeared, changed and disappeared over the course of days and weeks. The sun, like everything else in nature, was dynamic and imperfect. What Galileo could not have known is that these dark spots are actually cooler regions on the solar surface. While the surrounding photosphere blazes at nearly 10,000 degrees Fahrenheit, the center of a sunspot, the dark region called the umbra, may be only 6,300 degrees. This temperature difference is what makes them appear dark. They are not truly dark at all. If you could isolate a sunspot and view it against the blackness of space, it would glow with blinding intensity. It only appears dark because it is surrounded by even brighter material. But why are sunspots cooler? The answer lies in magnetism. Deep within the sun, in the churning convective zone where plasma rises and falls like boiling water, the rotation of our star twists and tangles its magnetic field lines. These field lines become concentrated in certain areas, and when they break through the surface, they inhibit the normal convection of heat from the interior. Think of it like placing a dam in a river. The magnetic field lines block the upward flow of heat, creating a region that is cooler than its surroundings. The magnetic field strength within a sunspot is extraordinary. While Earth's magnetic field measures approximately 1/2 of a Gauss at the surface, sunspots can have field strengths of 2,000 to 5,000 Gauss. This is thousands of times stronger than anything we experience on our planet, and it is this intense magnetic energy that makes sunspots so dangerous. Sunspots rarely appear alone. They typically form in pairs or groups, with each spot in a pair having opposite magnetic polarity. One spot acts like a magnetic north pole, the other like a south. Magnetic field lines arc between them, rising high into the solar atmosphere, the corona, before looping back down. When these field lines become twisted and tangled, when they cross and reconnect, enormous amounts of energy can be released in an instant. This is how solar flares are born. The magnetic reconnection releases energy equivalent to millions of nuclear bombs detonating simultaneously. X-rays and ultraviolet radiation blast outward at the speed of light, reaching Earth in just 8 minutes. Behind them comes a slower but far more dangerous threat, a coronal mass ejection, a billion-ton cloud of charged particles and magnetic fields racing through space at millions of miles per hour, aimed directly at our planet. The number of sunspots on the sun is not constant. It follows a cycle that astronomers have tracked for nearly 300 years. In 1755, the Swiss astronomer Johann Rudolf Wolff began systematically counting sunspots, establishing a numerical index that continues to this day. He discovered that sunspot numbers rise and fall over a period of approximately 11 years. During solar minimum, the sun may go days or even weeks without a single visible sunspot. The solar disk appears clean and quiet. But during solar maximum, dozens or even hundreds of spots can pepper the surface at any given time, and it is during solar maximum that the risk of dangerous solar storms reaches its peak. We are currently in solar cycle 25. It began in December of 2019, when the previous cycle reached its minimum. Scientists predicted it would be a relatively weak cycle, similar to the previous one, with a maximum of around 115 sunspots expected in July of 2025. But the sun had other plans. Solar cycle 25 has exceeded every prediction. Activity ramped up faster than expected. Sunspot numbers have been higher than forecast. In October of 2024, NASA and NOAA officially announced that the sun had reached solar maximum, but this was not just any maximum. The cycle produced the strongest geomagnetic storm in over 20 years, lighting up skies around the world with auroras visible as far south as Florida and northern California. In December of 2025, NASA's Solar Dynamics Observatory detected a sunspot region larger than any seen in a decade. The active region, labelled AR 4294 through 4296, spanned more than 10 times the width of Earth. Amateur astronomers captured filtered images showing the enormous dark patch rotating into view. Experts warned that this complex region had the potential to produce multiple powerful solar flares in the coming weeks, and the warnings proved accurate. On November 11th, 2025, the sun unleashed an X 5.1 solar flare, the strongest of the year. The blast originated from sunspot AR 4274, which had been producing powerful eruptions for days. The flare triggered radio blackouts across Africa and Europe, disrupting high-frequency communications. The accompanying coronal mass ejection raced toward Earth at 4.4 million miles per hour. Just weeks later, on December 31st, an M7.1 flare erupted from sunspot region AR 4324. The GOES-19 satellite captured stunning images of extremely hot flare plasma in the sun's corona. Forecasters predicted the associated coronal mass ejection would reach Earth by January 2nd or 3rd, potentially triggering strong geomagnetic storms as the new year began. The sun does not care about our calendars or our holidays. It does not know that we have built a civilization utterly dependent on electricity and electronics. It simply follows its own rhythms, its 11-year heartbeat of activity and quiet. And right now, that heart is beating faster than it has in decades. When you look up at the sun tomorrow morning, remember that you are looking at a nuclear reactor 400,000 times more massive than Earth. Remember that its surface is covered in dark magnetic storms, any one of which could spawn a flare powerful enough to disrupt everything we take for granted. Remember that we have built our entire world on the assumption that the sun will continue to behave. And remember that in 1859, we learned what happens when that assumption fails. But to understand the threat we face today, we must first travel back in time. Back to a September morning when a quiet English astronomer looked through his telescope and witnessed something that would change our understanding of the sun forever. Back to the moment when the modern world first learned that our star could reach out across 93 million miles and touch us with its fury. This is the story of the Carrington event, and it begins with a flash of white light. Chapter 2. A Storm from the Sun in 1859. The morning of September 1st, 1859 was clear and bright over the town of Redhill in Surrey, England. Richard Christopher Carrington climbed into his private observatory, a small structure attached to his country estate, and prepared for another day of solar observation. He had been studying the sun for years, meticulously recording the positions and movements of sunspots, trying to understand the patterns that governed their appearance and disappearance. Carrington was not a professional astronomer. He was a brewer by trade, having inherited his family's business. But his true passion lay in the heavens, and he had built one of the finest private observatories in England. His telescope was equipped with filters and projection screens that allowed him to safely observe the sun without destroying his eyesight. Day after day, he would sketch the dark spots on the solar disk, noting their positions, their shapes, their changes. On this particular morning, Carrington noticed an unusually large and complex group of sunspots near the center of the solar disk. He began to sketch them, carefully noting the darker umbral regions and the lighter penumbral areas surrounding them. It was routine work, the kind of observation he had made hundreds of times before, And then, at approximately 11:18 in the morning, something extraordinary happened. Two patches of intensely bright white light suddenly appeared within the sunspot group. Carrington later described them as kidney-shaped, blazing with a brilliance that far exceeded the already blinding solar surface. He stared in amazement, uncertain what he was seeing. Nothing like this had ever been recorded. Nothing like this was supposed to be possible. The bright patches moved, drifting across the face of the sunspot group over the course of about 5 minutes. Then, as suddenly as they had appeared, they began to fade. Within moments, they were gone entirely, leaving the sunspot group looking exactly as it had before. Carrington was stunned. He knew he had witnessed something significant, but he had no framework to understand what it meant. He rushed to find a witness, hoping someone else could confirm what he had seen. Unfortunately, by the time he returned to his telescope, the phenomenon had ended. What Carrington did not know, could not have known, is that he had just observed the first recorded solar flare in human history. That brilliant flash of white light was the visible signature of an enormous magnetic explosion on the sun's surface, and the consequences of that explosion were already racing toward Earth at nearly 1 million miles per hour. Approximately 18 hours later, the world began to change. On the night of September 1st and into the early hours of September 2nd, auroras appeared across the entire planet. These were not the gentle northern lights familiar to residents of Alaska and Scandinavia. These were apocalyptic displays of colour that reached down to the tropics. People in Cuba looked up and saw crimson curtains dancing across the sky. Observers in Panama witnessed green and red lights that seemed to set the heavens on fire. In Japan, in Australia, in Chile, people who had never seen an aurora in their lives stepped outside and stared in wonder and terror. In the Rocky Mountains of North America, gold miners woke in the middle of the night, convinced that dawn had arrived. The auroral glow was so bright that they began preparing breakfast at 1 in the morning, only to realize hours later that the sun had not yet risen. In the northeastern United States, people reported being able to read newspapers by the light of the aurora alone. But the beauty of the lights masked a more sinister reality. Around the world, the telegraph system, the high technology of the Victorian era, began to fail. The telegraph was the internet of the 1850s. It was the first technology that allowed instantaneous communication across vast distances. Messages that once took weeks to deliver by ship or horseback could now be sent in minutes. Financial markets depended on it. Governments depended on it. The world was becoming connected in ways that had never been possible before. And on the night of September 1st, 1859, that connection shattered. Telegraph operators reported sparks flying from their equipment. Some received severe electric shocks when they touched their machines. In several stations, the telegraph paper caught fire, set ablaze by mysterious currents flowing through the wires. The excess electrical energy in the atmosphere was inducing powerful currents in the long metal lines that crisscrossed the continents. In some cases, operators discovered that they could send and receive messages even with their batteries disconnected. The storm itself was providing enough electrical power to operate the telegraph. It was a terrifying demonstration of the energy that had been released by that brief flash of light Carrington had observed. The disruption lasted for days. Telegraph communication across Europe and North America was severely impaired. Some lines were damaged and required repair. Others simply refused to work properly until the storm subsided. The world's first global communication network had been temporarily crippled by a phenomenon that no one understood. In the aftermath, scientists struggled to make sense of what had happened. Carrington himself was cautious about drawing conclusions. He noted the coincidence between his observation of the solar flare and the subsequent geomagnetic disturbance, but he famously wrote that one swallow does not make a summer. He understood that correlation did not necessarily mean causation, but over the following decades, as more observations accumulated, the connection became undeniable. The sun was capable of producing explosions of light and energy that could travel across 93 million miles of space and affect conditions on Earth. The aurora and the telegraph failures were not supernatural events or divine interventions. They were the physical consequences of solar activity. What made the Carrington event so powerful? Modern analysis has revealed that multiple factors combined to create a perfect storm. First, the initial flare was extraordinarily intense, releasing vast amounts of energy in just a few minutes. Second, the resulting coronal mass ejection traveled at exceptional speed. While most CMEs take 2 to 4 days to reach Earth, the Carrington CME arrived in just 17.6 hours. This suggests it was traveling at roughly 1 million miles per hour, far faster than typical. Third, and perhaps most importantly, the Carrington CME may have been preceded by an earlier eruption that cleared a path through the solar wind. Normally, the space between the Sun and Earth is filled with a constant outflow of particles from the Sun. A CME must push through this material, which slows it down and dissipates some of its energy. But if an earlier CME has already swept the path clear, a following CME can travel faster and arrive with more of its energy intact. Scientists have found evidence in tree rings and ice cores that the Carrington event, while exceptional, was not unique. Similar or even larger events have occurred throughout Earth's history. A massive solar storm struck the planet in 774 to 775 of the Common Era, leaving a distinctive spike in carbon-14 levels preserved in ancient trees. This event may have been 10 to 20 times more powerful than the Carrington event. Even more extreme storms have been identified in the geological record. A solar event approximately 14,300 years ago may have exceeded all others. These so-called Miyake events, named after the Japanese scientist who first identified the 774 event, suggest that our sun is capable of producing storms far more powerful than anything witnessed in modern times. The Carrington event occurred in a world that was just beginning to electrify. Telegraph wires were the only significant conductors vulnerable to geomagnetically induced currents. The damage was inconvenient but ultimately manageable. Within days, the system was restored. Life continued. But what would happen if a Carrington-class event struck today? This is not an academic question. Scientists estimate that there is a 12% chance of a Carrington-level event occurring within the next decade. Some estimates are even higher, and the world of 1859 bears almost no resemblance to the world of today. In 1859, there were no electrical power grids, there were no satellites, there were no computers, no internet, no cell phones. The global economy did not depend on electronic transactions processed in milliseconds. Hospitals did not rely on electrically powered life support systems. Nuclear power plants did not need constant monitoring and cooling. Today, a storm of that magnitude would interact with an infrastructure that did not exist when Carrington looked through his telescope. The long-distance power lines that carry electricity across continents would act like giant antennas, collecting geomagnetically induced currents that could overload transformers. High-voltage transformers are the backbone of the electrical grid, and they are extremely vulnerable to this kind of damage. They are also expensive, difficult to manufacture, and can take more than a year to replace. A single powerful storm could damage hundreds of these transformers simultaneously. The resulting blackouts would not last hours or days. They could last weeks, months, or even years. And without electricity, everything stops. Water treatment plants fail, gas stations cannot pump fuel, food rots in warehouses with no refrigeration, hospitals go dark. In 2012, the world came terrifyingly close to finding out. A massive solar storm comparable in size and intensity to the Carrington event erupted from the sun in July of that year. It would have caused catastrophic damage to infrastructure worldwide, but we were lucky. The CME missed Earth by about 9 days' worth of orbital distance. It sailed harmlessly through the void where our planet had been just a week earlier. We dodged a bullet we did not even know was fired until it had passed. The Carrington event was a warning. It showed us that the sun is capable of violence on a scale we can barely comprehend. It demonstrated that our technology, however advanced, is vulnerable to forces beyond our control. And it proved that what has happened before can happen again. In 1859, the damage was limited and the recovery was swift. The next time may be very different. Because in the 166 years since Richard Carrington observed that flash of white light, we have built a civilization that depends entirely on the very technologies most vulnerable to solar storms, and the sun does not care. Chapter 3. The day Quebec went dark. March 13th, 1989, the day the sun brought darkness. In the early hours of that Monday morning, as most of Quebec slept, a powerful coronal mass ejection slammed into Earth's magnetic field. The CME had been travelling for nearly 2 days, launched by a series of massive solar flares from sunspot region 5395, one of the most active sunspot groups ever observed. In the week before the storm, this single region had produced more than a dozen M-class and X-class flares, hurling billions of tons of charged particles toward our planet. What happened next would become the most significant solar storm impact on a power system in history. At 2:44 in the morning Eastern Time, the geomagnetically induced currents flowing through Quebec's power grid found a weakness. The Hydro-Quebec system, which supplied electricity to the entire province, began to fail. Transformers overheated. Circuit breakers tripped. Protective relays, designed to prevent damage to equipment, began shutting down sections of the grid in a cascading sequence that moved faster than operators could respond. Within 90 seconds, the entire system collapsed. 6 million people woke to cold and darkness. Office buildings went black. Underground pedestrian tunnels became pitch dark. People found themselves trapped in elevators between floors. The Montreal Metro, the subway system that moved hundreds of thousands of commuters every day, shut down completely. Dorval Airport closed. Schools and businesses remained shuttered. For 9 hours, one of the largest and most modern electrical systems in North America was completely non-functional. The blackout was not limited to inconvenience. In March, nighttime temperatures in Quebec can drop well below freezing. Without electricity, heating systems failed. Without heating, pipes could freeze and burst. Without pumps, water treatment and distribution systems struggled to maintain pressure. Every hour that passed without power increased the risk of permanent damage to infrastructure and the potential for loss of life. Across the border in the United States, the storm was causing its own chaos. More than 200 power grid problems erupted within minutes of the geomagnetic storm's arrival. From coast to coast, utility operators scrambled to prevent the kind of cascading failure that had just devastated Quebec. In New Jersey, a high-voltage transformer was damaged by the induced currents. Circuit breakers tripped in states across the country. The United States came frighteningly close to experiencing widespread blackouts of its own. The only reason it did not was timing and luck. American utilities had just enough reserve capacity, and their grids were configured in ways that prevented the cascade from spreading. But the margin was thin, far too thin. Why was Quebec so vulnerable? The answer lies in geology and geography. Quebec sits on the Canadian Shield, one of the largest and oldest rock formations on the planet. This ancient granite bedrock has extremely low electrical conductivity. When geomagnetically induced currents flow through the Earth during a solar storm, they take the path of least resistance. In most places, that path runs through the ground itself. But on the Canadian Shield, the ground is too resistive. The currents seek other paths. They found them in the high-voltage power lines. The Hydro-Quebec system was designed to carry electricity from massive hydroelectric dams in the James Bay region, far to the north, down to the population centres in the south. This required extremely long transmission lines, some stretching more than 1,000 kilometres. These lines acted like giant antennas during the storm, collecting the induced currents and channeling them into the transformers and switching equipment. The combination was devastating. Low ground conductivity forced the currents into the power lines. Long transmission lines amplified the effect. And the single integrated grid, designed for efficiency and reliability under normal conditions, allowed the failure to spread instantly across the entire system. In space, satellites were tumbling out of control. NASA's TDRS-1 communication satellite recorded more than 250 anomalies as high-energy particles invaded its sensitive electronics. Even the Space Shuttle Discovery, which had launched just hours before the storm arrived, experienced mysterious problems. A sensor on one of its hydrogen tanks began showing abnormal pressure readings. The problem disappeared as mysteriously as it had appeared once the storm subsided. During the storm, auroras painted the sky as far south as Texas and Florida. Some observers initially feared a nuclear attack. Others believed they were witnessing some kind of supernatural event. The sky glowed red and green and purple, colors that residents of those southern states had never seen before and might never see again. For space weather researchers, the Quebec blackout was a watershed moment. Before March 13, 1989, few people outside specialized scientific circles understood that solar storms could affect power systems. The idea that the sun could turn off the lights seemed almost absurd. After the blackout, no one doubted it. Dr. David Boatler, who would later lead the Space Weather Group at Natural Resources Canada, called it the biggest geomagnetic storm of the space age. It became the archetypal disturbance for understanding how solar activity can cause blackouts. Every subsequent study of power grid vulnerability to space weather has used the 1989 event as a benchmark. Hydro-Quebec learned hard lessons that day. The utility spent more than $2 billion over the following 6 years implementing protective measures. They raised the trip levels on their protective relays, making the system less likely to shut down unnecessarily. They installed series compensation on their transmission lines to enhance grid stability. They established real-time monitoring systems to detect the early signs of geomagnetic disturbance and reduce power flows before damage could occur. The investments paid off. Since 1989, there have been multiple intense magnetic storms, some approaching or exceeding the intensity of the March 1989 event. None of them has caused a similar blackout in Quebec. The modern grid can handle a 1-in-100-year geomagnetic event. The March 1989 storm was estimated to be approximately a 1-in-50-year event. But the improvements in Quebec did not make the rest of the world immune. In 2003, a series of powerful solar storms struck Earth during the Halloween period. The so-called Halloween storms included some of the most powerful solar flares ever recorded. In Sweden, a power blackout left 50,000 people without electricity. In South Africa, transformers were damaged. Satellite operators around the world struggled to maintain control of their spacecraft. The Halloween storms demonstrated that, even with improved awareness and better monitoring, solar storms remained capable of causing significant damage, and they raised an unsettling question. What would happen during a storm that was not just a 1 in 50-year event, but a 1 in 500-year event? What would happen if something like the Carrington event struck our modern world? The March 1989 storm had a peak disturbance storm time index of negative 589 nanotesla. This index, known as DIST, measures how much the Earth's magnetic field is compressed during a geomagnetic storm. More negative values indicate more intense storms. The Carrington event is estimated to have had a DIST index between negative 800 and negative 1750 nanotesla. At the upper end of that range, it was roughly 3 times more intense than the March 1989 storm. Now consider what happened during that 90-second collapse in Quebec. Consider how close the United States came to experiencing similar blackouts. Consider the 200-plus grid problems that erupted simultaneously across North America. And then imagine a storm 2 or 3 times stronger. The March 1989 event was not a worst-case scenario. It was not even close. It was a moderate to strong storm that happened to hit a particularly vulnerable system at a particularly vulnerable time. The Carrington event was significantly more powerful, and the Miyake events recorded in tree rings were more powerful still. We have built a global civilization that depends on continuous electrical power. Our food systems, our water systems, our communication systems, our financial systems, our healthcare systems all require electricity to function. Oh, prolonged widespread blackout would not simply be inconvenient, it would be catastrophic. The Quebec blackout lasted 9 hours. What if it had lasted 9 days, 9 weeks, 9 months? After the storm of March 1989, engineers and policymakers began to take the threat seriously. New monitoring systems were deployed, new protective standards were developed, new research initiatives were launched. We learned that solar storms were not just a curiosity for scientists, they were a genuine threat to the infrastructure that modern society depends on. But the improvements have been incremental. The investments have been modest compared to the scale of the risk. And the sun continues its 11-year cycle, sometimes quiet, sometimes violent, entirely indifferent to the civilization we have built beneath its light. March 13th, 1989 proved that solar storms can bring down power grids. It proved that the failure can happen faster than humans can respond. And it proved that the consequences extend far beyond flickering lights and inconvenience. 6 million people spent that cold March night in darkness. They were the lucky ones. They lived in a time and place where help was available, where the failure was localized, where recovery took hours rather than months. The next time might be very different. The sun gave us a warning that day. The question is whether we have truly heard it. Chapter 4. Solar Cycle 25 and the Maximum. The sun has a heartbeat, not a pulse of blood through arteries, but a rhythm of magnetic activity that rises and falls over approximately 11 years. At the start of each cycle, the sun is quiet. Few sunspots mark its surface. Solar flares are rare and typically weak. The corona, the outer atmosphere of the sun, appears calm and stable. Then, gradually, activity begins to build. Sunspots appear at higher latitudes and slowly drift toward the equator as the cycle progresses. The magnetic field becomes more complex, more twisted, more prone to violent release. Solar flares occur with increasing frequency. Coronal mass ejections blast outward into the solar system. The sun enters its restless phase. At solar maximum, the star reaches its peak of activity. Sunspots pepper the surface in numbers not seen during quieter years. Powerful flares erupt regularly, sometimes multiple times per day. The risk of severe space weather events affecting Earth reaches its highest point. And then, just as gradually as it began, the activity starts to decline. The cycle winds down toward the next minimum, and the pattern begins again. Scientists have been tracking these cycles since 1755, when astronomers began systematically counting sunspots. We are currently in solar cycle 25, the 25th cycle since regular observations began, and this cycle has surprised everyone. When solar cycle 25 began in December 2019, the scientific consensus was clear. The cycle would be weak to moderate, similar to the relatively quiet solar cycle 24 that had preceded it. The solar cycle 25 prediction panel, an international group of experts co-sponsored by NASA and NOAA, forecast a maximum of around 115 sunspots occurring in July 2025. Some researchers even speculated that we might be entering a prolonged period of reduced solar activity, possibly similar to the Maunder minimum of the 17th century when sunspots virtually disappeared for decades. The sun had other plans. From the very beginning, solar cycle 25 exceeded expectations. Activity ramped up faster than predicted. sunspot numbers consistently ran higher than the forecast curves. By January 2023, just 3 years into the cycle, solar cycle 25 had already surpassed solar cycle 24 at the equivalent point. The increase was not subtle, it was unmistakable. The powerful storms of May 2024 forced the scientific community to acknowledge that their predictions had been too conservative. During the first full week of May, a barrage of large solar flares and coronal mass ejections launched toward Earth. The active regions responsible, designated AR 13663 and AR 13664, produced 82 notable solar flares in just 7 days. 9 of these were classified as X-class, the most powerful category of solar flare. The CMEs arrived at Earth starting May 10th, bunching up in waves due to the rapid-fire nature of the eruptions. They created a geomagnetic storm that reached G5 on the Noe scale, the highest rating possible. It was the first G5 storm since 2003, and it produced one of the most spectacular auroral displays in recorded history. People across the world looked up and saw something extraordinary. In North America, auroras were visible from states that almost never see them: Florida, Texas, New Mexico, Arizona. Even observers in the Florida Keys and the Yucatan Peninsula in Mexico reported seeing colors dancing across the night sky. Across Europe, aurora sightings extended as far south as Portugal, Spain, and Sardinia. In Africa, observers in Algeria and the Canary Islands witnessed the display. Throughout Asia, from Turkey to Japan to northern India, people photographed the lights. By one measure, these auroras may have been among the strongest in 500 years. Scientists estimated that they were visible at magnetic latitudes as low as 26 degrees, rivaling historical accounts from events like the Carrington storm of 1859. On October 15th, 2024, NASA and NOAA made it official. The Sun had reached solar maximum. The announcement came with an important caveat. This did not mean solar activity had peaked. The month of maximum sunspot numbers would not be identifiable until at least 7 months later, after scientists could confirm a consistent decline. Solar cycles can experience double peaks, with activity rising and falling before rising again. The 2024 announcement simply confirmed that we were in the maximum phase. As the announcement was being made, the Sun was already preparing its next assault. Just days later, a series of powerful flares erupted, including an X7.1 on October 1st and an X9.0 on October 3rd. These were among the strongest flares of the cycle. November 2025 brought more violent activity. On November 4th, the Sun fired off 2 X-class flares in less than 12 hours, causing radio blackouts across the Americas and Pacific. On November 11th, an X5.1 flare erupted from sunspot region AR4274, the strongest flare of 2025 at that point. It triggered R3-level radio blackouts across Africa and Europe and hurled another CME toward Earth. The November storms produced another round of spectacular auroras. On November 11th and 12th, the northern lights were visible across much of the northern United States, the United Kingdom, and continental Europe. A geomagnetic storm classified as G3, potentially approaching G4, rattled satellite operators and power grid managers around the world. December brought the largest sunspot region in a decade. Active region 4294 through 4296 rotated into view on December 1st, revealing a dark patch more than 10 times the width of Earth. Amateur astronomers captured filtered images showing the enormous structure. Experts warned that the complex magnetic configuration made it a prime candidate for powerful X-class flares. The warnings proved justified. On December 1st, an X1.9 flare erupted from the region, causing significant radio blackouts in Australia. M-class and C-class flares followed in rapid succession throughout the month. As the year ended, forecasters were tracking multiple CMEs expected to reach Earth in the first days of January 2026. This is what solar maximum looks like. This is the Sun at its most violent and unpredictable. And despite the official announcement that maximum has been reached, scientists caution that the most dangerous period may not be over. Historically, powerful solar events can occur well into the declining phase of a solar cycle. Some of the most destructive storms on record have struck years after the official maximum. The period from late 2024 through 2025 has demonstrated that our Sun is capable of producing storms that rival historical events. The May 2024 G5 storm was the strongest in over 2 decades. It disrupted GPS signals enough to affect precision farming operations that depend on centimetre-level accuracy. It forced satellite operators to implement protective measures. It demonstrated that even with modern monitoring and forecasting, the Sun can still catch us off guard. Yet for all its fury, the May 2024 storm did not cause catastrophic damage. Power grids remained operational, Satellites were protected. The precautions implemented after past storms worked as designed. Some observers breathed a sigh of relief, interpreting the limited damage as evidence that we have the threat under control. This interpretation is dangerously optimistic. The May 2024 storm was powerful, but it was not a Carrington-class event. Estimates of its peak DIST index range from -412 to -518 nanotesla. Severe? Yes. Historic by recent standards? Yes. But the Carrington event may have reached -1750 nanotesla. We have not yet faced a truly extreme storm in the modern era. Solar Cycle 25 has also revealed how much remains uncertain about our star. The official predictions failed significantly. The cycle has been at least 30% more active than Solar Cycle 24 at equivalent points. The mechanisms that determine whether a cycle will be strong or weak remain poorly understood. We cannot reliably predict how intense activity will become or when the most dangerous events will occur. What we do know is sobering. The Sun has reached maximum phase. Activity is expected to remain elevated through at least 2025 and possibly into 2026. The risk of severe geomagnetic storms remains high, and somewhere on the surface of our star, magnetic field lines are twisting and building energy, preparing for the next eruption. The current solar maximum is not the apocalyptic event that some feared, but it is a reminder that we live at the mercy of a star we barely understand. The same sun that makes life possible can, with a single, well-aimed explosion, disrupt the technological infrastructure that modern civilization depends on. We are watching, we are monitoring, we are preparing, but we cannot control what the sun does next. Chapter 5. The Mechanics of Solar Violence. To understand the threat the sun poses to our civilization, we must first understand how our star attacks. The violence begins deep within the sun, in the churning convective zone where superheated plasma rises and falls in constant motion. This movement, combined with the sun's rotation, generates powerful electric currents that produce the solar magnetic field. But the sun does not rotate like a solid ball. The equator spins faster than the poles. This differential rotation stretches and twists the magnetic field lines over time, winding them tighter and tighter, like a rubber band being wound around a spool. The field becomes increasingly complex, increasingly stressed, increasingly unstable. Eventually something has to give. When magnetic field lines become too twisted, they can reconnect in different configurations, releasing enormous amounts of stored energy in a fraction of a second. This process, called magnetic reconnection, is the engine that drives solar flares. The energy released heats plasma to tens of millions of degrees and accelerates particles to near the speed of light. X-rays and extreme ultraviolet radiation blast outward from the reconnection site. A solar flare is an explosion of light. It spans the entire electromagnetic spectrum, from radio waves to gamma rays. The most energetic flares release enough energy to power human civilization for millions of years. They are the largest explosions in our solar system. Scientists classify solar flares according to their intensity using a letter scale. A-class flares are the weakest, barely distinguishable from the sun's background radiation. B-class flares are slightly stronger. C-class flares are common during active periods and can cause minor radio disturbances. M-class flares are moderate events that can cause brief radio blackouts and pose radiation risks to astronauts. And then there are X-class flares. X-class flares are the most powerful explosions the sun produces during normal activity. The designation works like the Richter scale for earthquakes. An X2 flare is twice as powerful as an X1. An X10 is 10 times more powerful. The scale has no upper limit. During Solar Cycle 25, we have witnessed flares exceeding X9, among the strongest recorded since systematic observation began. When an X-class flare erupts from an Earth-facing sunspot, the consequences begin within minutes. The burst of electromagnetic radiation travels at the speed of light, reaching our planet in just 8 minutes. X-rays and extreme ultraviolet photons slam into Earth's upper atmosphere, ionizing gas molecules in the ionosphere and temporarily changing its structure. High-frequency radio communications that depend on bouncing signals off the ionosphere are disrupted or blocked entirely. These radio blackouts are classified on an R1 through R5 scale. R1 is minor, affecting high-frequency radio on the sunlit side of Earth for a few minutes. R5 is extreme, causing complete blackout of high-frequency communications for hours, affecting aviation, maritime operations, and emergency services. R3 events classified as strong can disrupt communications for an hour or more. But the flare itself is only part of the story. Often the same magnetic reconnection that produces a solar flare also launches something far more dangerous into space. A coronal mass ejection is not a flash of light. It is a physical object, a massive cloud of plasma and magnetic fields ripped from the Sun's corona and hurled into the solar system. A single CME can contain billions of tons of material traveling at speeds ranging from 250 kilometers per second to more than 3,000 kilometers per second. The fastest CMEs can cover the 93 million miles between the Sun and Earth in less than 18 hours. Unlike the electromagnetic radiation of a flare, which affects Earth almost immediately, a CME takes time to arrive. This delay is crucial. It gives us a warning window, typically between 1 and 3 days, during which we know a potentially dangerous cloud of plasma is headed our way. Modern spacecraft stationed at the L1 Lagrangian point, about 1 million miles sunward of Earth, can detect an approaching CME roughly 30 to 60 minutes before it arrives. This final warning allows satellite operators and power grid managers to implement last-minute protective measures. When a CME reaches Earth, it interacts with our planet's magnetic field in complex ways. The impact depends heavily on the orientation of the magnetic field carried by the CME. Earth's magnetic field points northward at the equator. If the CME's magnetic field is also pointing northward, it tends to slide around the magnetosphere without significant coupling. The storm may be relatively mild, but if the CME's magnetic field points southward, opposite to Earth's field, something different happens. The opposing fields can connect and reconnect at the boundary of the magnetosphere, opening pathways for solar plasma and energy to pour into near-Earth space. This process transfers enormous amounts of energy into the magnetosphere, driving the geomagnetic storms that can damage satellites, disrupt communications, and overload power grids. The intensity of a geomagnetic storm is measured by the KP index, which runs from 0 to 9, or by the NOAA G scale, which runs from G1 to G5. A G1 storm is minor, producing weak power grid fluctuations and minor effects on satellite operations. A G3 storm is strong, potentially causing voltage irregularities in power systems and requiring satellite operators to take corrective actions. A G5 storm is extreme, capable of causing widespread voltage control problems, complete high-frequency radio blackout, and satellite damage. The mechanisms of damage differ depending on the technology affected. Satellites in orbit face multiple threats during a geomagnetic storm. High-energy particles can penetrate spacecraft electronics, causing bit flips in computer memory and potentially triggering software failures or permanent hardware damage. The increased solar radiation heats and expands Earth's upper atmosphere, increasing drag on low-orbit satellites and altering their trajectories. The changing magnetic environment can confuse attitude control systems. During the May 2024 G5 storm, NASA and commercial satellite operators implemented protective procedures that successfully prevented significant damage, but the margin for error was slim. Power grids face a different kind of threat. When a geomagnetic storm disturbs Earth's magnetic field, it induces electric currents in the ground. These geomagnetically induced currents, or GICs, flow through any conductive path available to them, including the grounding systems of high-voltage transformers. The currents can push transformers into saturation, causing them to overheat and potentially destroying their core windings. Large power transformers are the backbone of the electrical grid, and they are particularly vulnerable. They are expensive, often costing tens of millions of dollars. They are difficult to manufacture, requiring specialized facilities, and they can take 12 to 18 months to build and deliver. A geomagnetic storm that damages multiple transformers simultaneously could leave regions without power for extended periods, while replacements are manufactured. The threat to transformers depends on several factors. The intensity and duration of the geomagnetic storm matters. The design and age of the transformer matters. The geological conductivity of the ground matters, and the length and orientation of the transmission lines feeding the transformer matters. Long lines running north to south are particularly vulnerable because they align with the flow of induced currents. GPS and navigation systems face disruption during solar storms because the ionosphere through which GPS signals must pass becomes turbulent and unpredictable. The ionosphere normally delays GPS signals by a predictable amount, which receivers can correct for. But during a geomagnetic storm, the ionosphere becomes irregular, with patches of different density that delay signals by varying amounts. This introduces errors in position calculations that can exceed safe tolerances for precision applications. During the May 2024 storm, the agricultural equipment company John Deere reported that customers relying on GPS-guided tractors experienced significant disruptions. Precision farming requires centimeter-level accuracy for applications like automated planting and spraying. Storm-induced GPS errors made this impossible, forcing some farmers to halt operations during critical planting season. Aviation faces risks during strong solar storms as well. High-frequency radio, which pilots and air traffic controllers use for communication over oceans and remote areas, can be blacked out for hours. Solar radiation storms can increase radiation exposure for passengers and crew on polar routes. Some airlines reroute flights away from polar regions during intense solar events to reduce crew exposure. Understanding these mechanisms is essential because it reveals both our vulnerabilities and our opportunities for protection. We cannot stop the sun from producing flares and CMEs, but we can design more resilient systems. We can implement protective procedures. We can monitor solar activity and prepare for incoming storms. Knowledge of how solar violence affects Earth gives us the tools to defend ourselves. The sun will continue its cycles of activity and quiet. Magnetic field lines will continue to twist and reconnect. Flares will continue to erupt and CMEs will continue to race through space. The question is not whether another powerful storm will strike Earth. The question is whether we will be ready when it does. Chapter 6. When the grid goes down. Imagine waking in the middle of the night to absolute darkness. No glow from streetlights filtering through your curtains. No hum from your refrigerator. No tiny LED indicators on your smoke detectors or charging devices. Just darkness and silence so complete that for a moment you wonder if you have gone blind. You reach for your phone to check the time. The screen lights up showing 3:14 in the morning. The battery indicator shows 42%. Good. You will have light for a few hours at least. You assume a transformer blew somewhere nearby, that crews are already working to restore power, that by morning everything will be back to normal. But morning comes, and the power does not return, nor does it return by noon, or by evening, or the next day, or the next week. This is what a catastrophic grid failure looks like from the inside. Not a dramatic explosion or visible destruction, but a creeping realization that the invisible infrastructure you depended on without thinking has simply stopped working, and with it, everything else begins to fail. The electrical grid is not a luxury. It is the foundation upon which modern civilization rests. Every other system we depend on either runs on electricity directly or depends on systems that do. When the grid fails, the cascade of consequences extends far beyond dark rooms and spoiled food. Water treatment plants require electricity to operate pumps, filtration systems, and chemical dosing equipment. Most municipal water systems maintain enough pressure in their pipes to continue delivering water for a few hours after power fails. But without electricity to run the pumps, that pressure eventually drops to zero. In tall buildings, water may stop flowing within minutes as the pressure becomes insufficient to reach upper floors. Wastewater treatment faces similar challenges. Without power, sewage pumping stations cannot move waste through the system. In many cities, gravity will continue to drain sewage from homes and businesses for a time, but eventually the system backs up. Raw sewage begins to overflow from manholes and storm drains. The risk of waterborne disease increases dramatically. Gas stations cannot pump fuel without electricity. Even stations equipped with backup generators have limited fuel supplies and will eventually run dry. Within days of a widespread power outage, personal vehicles become useless for most people. The roads may remain passable, but there is no way to fill the tank. The food distribution system depends on refrigeration at every stage. Warehouses, trucks, grocery stores, and home refrigerators all require electricity to keep food from spoiling. A large grocery store may have enough inventory to last a few days under normal conditions, but without refrigeration, perishable items begin to spoil within hours. Meat, dairy, produce, and frozen goods become unsafe to eat. Only shelf-stable items remain viable. Hospitals present one of the most acute challenges during extended blackouts. Modern medical care depends entirely on electricity. Ventilators, heart monitors, dialysis machines, imaging equipment, surgical tools, and countless other devices require power to function. Most hospitals have backup generators that can run for 24 to 72 hours on stored fuel. After that, they face impossible choices. Communication systems fail in stages. Cell towers typically have battery backup that lasts 8 to 12 hours. After the batteries drain, the towers go dark. Landline telephone systems may last longer in some areas, but they too depend on powered equipment in switching centers. Internet service requires powered routers, switches, and servers at every link in the chain. Within a day or two of a widespread blackout, most people lose the ability to communicate with anyone beyond shouting distance. Financial systems grind to a halt almost immediately. Credit card transactions require electronic authorization. ATMs require power. Bank branches cannot access account information. The complex web of electronic transactions that moves trillions of dollars daily simply stops. Cash becomes the only functional currency, and most people do not keep significant cash on hand. This is the reality we face if a severe geomagnetic storm damages enough of the electrical grid to cause prolonged widespread outages. The question is not whether such a storm could occur. History proves that it can. The question is how long the outage would last and how wide an area would be affected. A 2008 study by the National Academy of Sciences examined the potential consequences of a severe geomagnetic storm on the United States power grid. The findings were sobering. The study estimated that a Carrington-class event could damage or destroy more than 300 large power transformers across the country. The resulting blackouts could affect more than 130 million people, and because of the long lead time required to manufacture replacement transformers, the outages could last from 4 months to as long as 10 years in some areas. The economic impact would be staggering. The same study estimated costs between $1 trillion and $2 trillion in the first year alone. A 2013 analysis by Lloyds of London and Atmospheric and Environmental Research put the potential cost to the United States of a Carrington-class event at $600 billion to $2.6 trillion. These figures do not include the human cost in lives lost due to failed medical care, contaminated water, food shortages, and civil unrest. More recent research has examined secondary effects that extend beyond direct infrastructure damage. A study published in the journal Economics of Disasters and Climate Change explored the impact on agriculture. A severe geomagnetic storm that disrupts industrial production would also disrupt the supply of agricultural inputs like fertilizers and pesticides. The researchers estimated that this indirect effect could reduce global crop yields by 38 to 48%, with some regions like Central Europe experiencing yield losses up to 75%. The vulnerability is not distributed evenly. Some regions of the world are more exposed than others. Areas with long transmission lines, low ground conductivity, and older transformer designs face the greatest risk. Northern latitudes experience stronger geomagnetic disturbances because they are closer to the auroral zone where storm currents concentrate. Coastal regions with underlying igneous rock, which has low electrical conductivity, force more induced current into power lines. The northeastern United States and eastern Canada are particularly vulnerable due to their geology and grid configuration. Scandinavia faces similar risks. Parts of China and Japan have experienced transformer damage from past storms. No industrialized region is completely immune. What makes this threat different from other disaster scenarios is the potential for simultaneous failure across vast areas. Earthquakes, hurricanes, and floods cause localized destruction. Neighboring regions can send aid, equipment, and personnel to help with recovery. But a severe geomagnetic storm affects entire continents at once. There is no unaffected neighbor to call for help. Everyone is dealing with the same crisis simultaneously. The interdependence of modern infrastructure amplifies the problem. Power plants require fuel deliveries that depend on functioning transportation networks. Transportation networks require fuel that must be pumped using electricity. Refineries that produce fuel require electricity to operate. Communication systems that coordinate emergency response require power. Each system depends on other systems that also depend on power. This is not a problem that can be solved simply by stockpiling supplies or preparing individual households. While personal preparedness is valuable, the scale of a Carrington-class event exceeds what individuals can manage on their own. A functioning society requires functioning infrastructure. When that infrastructure fails across an entire continent, the recovery requires coordinated effort at a scale never before attempted. The good news is that we are not helpless. Engineers have developed technologies to protect transformers from geomagnetically induced currents. Neutral blocking devices can prevent damaging currents from entering transformer windings. Protective relays can be configured to detect GIC signatures and take defensive action. Operators can reduce power flows and disconnect vulnerable equipment when storms approach. The bad news is that these protections have not been universally deployed. Implementation has been uneven, driven more by individual utility decisions than coordinated national policy. Some grids are far better protected than others. Some transformers have been hardened against GIC damage, while others remain vulnerable. The patchwork nature of the improvements means that a severe storm could still find weak points to exploit. We have built a civilization that runs on electricity. We have made that electricity flow through a grid that was designed for efficiency and economy, not resilience against space weather. And we have created interdependencies so complex that failure in one sector cascades rapidly into failures in every other sector. The question is not whether the grid could fail catastrophically. The question is what we are willing to do to prevent it. Chapter 7. The Invisible Shield Above Us. Every second of every day, the sun hurls approximately 1 million tons of charged particles into space. This constant outflow, the solar wind, races through the solar system at speeds exceeding 1 million miles per hour. It carries with it the sun's magnetic field, stretched and twisted into a vast spiral that extends far beyond the orbit of Pluto. If this relentless bombardment struck Earth directly, The consequences would be catastrophic. The charged particles would strip away our atmosphere over geological time, just as they stripped away the atmosphere of Mars billions of years ago. The radiation would make the surface uninhabitable for complex life. Earth would be a dead world, its oceans boiled away, its surface scoured by the unfiltered fury of our star. But we are protected, and the protection comes from deep within our own planet. Approximately 1,800 miles beneath your feet, surrounding Earth's solid iron inner core, lies a layer of liquid iron and nickel. This outer core churns and flows, driven by heat escaping from the inner core and the rotation of the planet. The movement of this electrically conductive fluid generates powerful electric currents, and those currents produce Earth's magnetic field. This process, called the geodynamo, has been operating for at least 3.5 billion years. The magnetic field it generates extends far into space, creating a vast bubble called the magnetosphere. On the side facing the Sun, the magnetosphere is compressed by the pressure of the solar wind, reaching out to approximately 40,000 miles. On the night side, it stretches into a long tail that extends millions of miles into space, like a comet's tail pointing away from the Sun. The question is whether our Sun is capable of producing such events. For many years, scientists believed the Sun was too stable and too magnetically quiet to generate true superflares. Our star seemed to be in a different category from the hyperactive stars producing extreme events. But recent observations have complicated this picture. Studies of Sun-like stars have found that some superflare producers have activity levels comparable to, or even lower than our Sun. The discovery of Miyake events proved that our Sun has produced events far stronger than anything in the modern record. The possibility that our star could produce a superflare can no longer be dismissed entirely. Researchers at Harvard estimated the frequency of various types of solar events and their potential consequences. They found that extinction-level superflares, events powerful enough to erode significant portions of Earth's atmosphere or damage the ozone layer severely, occur approximately once every 20 million years. This is rare on human timescales, but has certainly happened multiple times in Earth's history. Some scientists have even proposed that extreme solar events may have contributed to past mass extinctions. One hypothesis suggests that a supersolar proton event approximately 12,800 years ago could have played a role in the extinction of Pleistocene megafauna. The evidence is controversial and not widely accepted, but it illustrates that researchers are taking seriously the possibility of biologically significant solar events. At the extreme end of theoretical possibility, a sufficiently powerful superflare could damage Earth's ozone layer, allowing increased ultraviolet radiation to reach the surface. It could inject massive amounts of nitrogen oxides into the stratosphere, further depleting ozone and potentially triggering climatic effects. It could produce radiation levels high enough to pose direct health risks to organisms on the surface. But even these extreme scenarios would not sterilize the planet. Life has survived worse. The asteroid impact that killed the dinosaurs was far more destructive than any solar event our star could plausibly produce. And life not only survived but eventually flourished again. The threat from the Sun is not extinction of all life. It is the potential disruption or collapse of human civilization. We have built a world that depends on constant supplies of electricity, continuous communication, and global coordination. We have created systems so complex and interconnected that failures cascade in ways that are difficult to predict and harder to stop. A severe solar storm would not kill everyone directly, but it could kill the systems that keep everyone alive, and that is a distinction that may not matter much to the people caught in the collapse. The probability of a civilization-threatening solar event in any given year is low, but over decades and centuries, the probability accumulates. Scientists estimate there is roughly a 1 to 12% chance of a Carrington-class event in the next decade. The chance of a Miyake-class event in any given century is harder to estimate but is clearly not zero. We cannot prevent solar storms. We cannot control when they occur or how powerful they will be. We can only prepare for them, building resilience into our systems and developing the ability to recover quickly when damage occurs. The Sun will not end all life on Earth, but it could end life as we know it. The difference between those two outcomes depends entirely on what we choose to do now. Chapter 9. Preparing for the next big one. The Sun does not give us much warning. A solar flare erupts and its radiation reaches Earth in 8 minutes. A coronal mass ejection launches from the Sun, and we have perhaps 1 to 3 days before it arrives. The final confirmation of a CME's intensity and magnetic orientation comes only 30 to 60 minutes before impact, when spacecraft stationed at the L 1 million miles sunward detect the incoming storm. This is not much time to prepare, but it is enough if we have done our homework. The Space Weather Prediction Center in Boulder, Colorado operates around the clock, 365 days a year. Forecasters monitor data streaming in from a fleet of spacecraft watching the sun, including NASA's Solar Dynamics Observatory, the SOHO satellite, and NOAA's GOES satellites in geostationary orbit. They track active regions on the solar surface, assess the probability of flares, and model the trajectories of coronal mass ejections when they erupt. When a potentially dangerous event occurs, the center issues alerts, watches, and warnings to an extensive list of stakeholders. Power grid operators receive notification that geomagnetic storm conditions are expected. Satellite operators learn that elevated radiation levels may affect their spacecraft. Airlines are warned about potential impacts on polar routes. Emergency managers begin preparing for possible disruptions. This early warning system has improved dramatically since the 1989 Quebec blackout. New satellites have been launched with better instruments. Forecasting models have become more sophisticated. Communication protocols have been established to ensure warnings reach the people who need them. NOAA's Deep Space Climate Observatory, positioned at the L1 point, provides real-time monitoring of the solar wind approaching Earth. When a CME arrives at the spacecraft, sensors measure its speed, density, and magnetic field orientation. This information is transmitted to Earth, giving operators their final warning that a storm is about to hit and how intense it is likely to be. The GOES R-series satellites, including GOES 16 through 18, carry sophisticated instruments that monitor solar activity in multiple wavelengths. They can detect solar flares within seconds of their occurrence and provide detailed imagery of coronal mass ejections as they launch from the sun. The data feeds directly into the forecasting models that predict storm intensity and timing. But monitoring and forecasting are only part of the solution. The real challenge is what we do with the warnings we receive. Power grid operators have developed operational procedures for space weather events. When a severe geomagnetic storm is expected, they can reduce power flows on vulnerable transmission lines, decreasing the current available to be pushed through by induced fields. They can bring additional generation capacity online to maintain grid stability. They can suspend maintenance activities that might make the system more vulnerable. They can position crews and equipment to respond quickly if damage occurs. Hydro-Quebec, the utility that suffered the catastrophic 1989 blackout, has become a leader in space weather preparedness. After spending $2 billion on system improvements, the utility has weathered multiple intense storms without significant incident. Their experience demonstrates that vulnerability can be reduced through targeted investment and operational discipline. Hardware solutions are also being deployed. Neutral blocking devices can be installed at the base of large transformers to prevent geomagnetically induced currents from flowing through the transformer windings. These devices work by inserting a capacitor in the neutral connection, which blocks the quasi-DC induced currents while allowing normal alternating current to flow. The Western Area Power Administration installed its first neutral blocking device at White Substation in South Dakota in November 2022. When a moderate geomagnetic storm struck in February 2023, the device activated automatically, successfully protecting the transformer from induced currents. The technology works. The challenge is deploying it widely enough to make a difference during a truly severe event. Some utilities have begun stockpiling spare transformers and critical components. Large power transformers are difficult to manufacture and can take more than a year to deliver under normal circumstances. During a crisis affecting multiple utilities simultaneously, that timeline would only grow longer. Having spares already in position dramatically reduces recovery time. The satellite industry has developed its own protective measures. Spacecraft can be placed in safe mode during intense storms, shutting down sensitive instruments and orienting to minimize radiation exposure. Operators can delay sensitive maneuvers until storm conditions pass. Designs have been improved to make electronics more resistant to radiation-induced failures. GPS operators have implemented enhanced monitoring during solar storms. When ionospheric disturbances degrade positioning accuracy, warnings can be issued to users who depend on high precision. Some applications can automatically fall back to other navigation methods or alert operators that GPS accuracy is temporarily compromised. At the international level, coordination has improved. The International Space Environment Service brings together space weather agencies from around the world to share data and coordinate warnings. The United Nations Committee on the Peaceful Uses of Outer Space has recognized space weather as a global concern requiring international cooperation. When a severe storm threatens Earth, it will affect the entire planet, and the response must be similarly global. In the United States, a national space weather strategy and action plan coordinates efforts across multiple federal agencies. NASA provides research and improved understanding of solar physics. NOAA operates the forecasting and warning systems. The Department of Homeland Security works with critical infrastructure operators to improve resilience. The Department of Energy supports research on grid protection technologies. FEMA prepares for the emergency response that would be required if a severe storm caused widespread damage. Individual preparedness also plays a role. Households that maintain supplies of water, food, batteries, and cash will be better positioned to weather a prolonged power outage regardless of its cause. Communities that have identified vulnerable populations and developed plans to assist them will recover more quickly. Organizations that have tested their backup systems and trained their personnel will experience less disruption. But we must be honest about the limits of our preparedness. The improvements made since 1989 have addressed the threat of moderate to strong geomagnetic storms. They have not fully addressed the threat of an extreme event like the Carrington storm or worse. The cost of protecting the entire North American power grid against a Carrington-class event has been estimated at several $billion. This is a small fraction of the potential damage such an event could cause, but it is still a substantial investment. Progress has been incremental, driven more by individual utility decisions than by comprehensive national policy. Some parts of the grid are well protected, others remain vulnerable. The transformer supply chain remains a potential choke point. Global manufacturing capacity for large power transformers is limited. Most units are custom-built for specific applications. A severe storm that damages hundreds of transformers simultaneously would create a shortage that could take years to resolve. There is also the challenge of events that exceed our models. Our protective standards are based on what we have observed and what we can simulate. A Miyake-class event, far more powerful than anything in the modern record, might overwhelm systems designed for lesser storms. We are preparing for events we have experienced or can imagine. We may not be prepared for events that exceed our imagination. The work continues. New satellites are being developed with improved monitoring capabilities. Forecasting models are being refined with better physics and more data. Grid operators are implementing new protective measures and testing their response procedures. The scientific community is studying ancient records to better understand the range of events our sun can produce. We are making progress. We are better prepared today than we were in 1989, and we will be better prepared tomorrow than we are today. But the sun does not grade on a curve. It does not care whether we have done our best. When the next great storm comes, we will either be ready or we will not. The warning systems will give us hours or days of notice. What we do with that notice depends on the preparations we make now. Chapter 10. The Price of Our Electric World. The sun rose this morning as it has risen every morning for 4.5 billion years. It will rise again tomorrow, and the day after, and for another 5 billion years until it exhausts its hydrogen fuel and swells into a red giant that consumes the inner planets. On astronomical timescales, the sun is stable and predictable. On human timescales, it is the most reliable force in our existence. And yet, somewhere on the surface of that familiar yellow disk, magnetic field lines are twisting and building energy. They have been doing this since before humans existed. They will continue doing it long after we're gone. Most of the time, this activity produces nothing more than beautiful auroras dancing over polar skies. Occasionally, it produces something more. We have built our civilization on an assumption. We have assumed that the constant flow of electricity through our grids will continue uninterrupted. We have assumed that our satellites will continue orbiting and transmitting. We have assumed that the sun, while occasionally temperamental, will never truly threaten the technological infrastructure we depend on. This assumption has served us well. For more than a century, we have electrified our world, connecting billions of people to power grids, communication networks, and information systems that would have seemed like magic to our ancestors. We have built wonders. We have eradicated diseases. We have fed populations that earlier generations could not have imagined. And we have created vulnerabilities that earlier generations could not have imagined either. The irony is exquisite. The same sun that makes life possible, that drove the evolution of photosynthesis and powered the food chain that culminated in human consciousness, is also the greatest natural threat to the civilization that consciousness has built. We depend on the sun, absolutely, and we are vulnerable to the sun, absolutely. The relationship is not one of equals. We receive the sun's gifts and endure its violence without any ability to influence either. The sunspots visible on the solar surface right now are reminders of this relationship. They are dark because they are cooler than their surroundings, but the coolness is relative. A sunspot is still thousands of degrees hot. It would vaporize anything that touched it. And the magnetic complexity within those dark regions holds energy sufficient to power millions of nuclear weapons, waiting to be released in an instant. We cannot prevent solar storms. We cannot negotiate with the sun. We cannot build a wall that keeps out coronal mass ejections or deploy a defense system that shoots down solar flares. The sun will do what it will do, following the physics of magnetic reconnection and plasma dynamics, utterly indifferent to the civilization in its path. What we can do is choose how we respond to this reality. We can choose to build resilience into our systems. We can design power grids that fail gracefully rather than catastrophically. We can install protective devices on vulnerable transformers. We can maintain reserves of critical equipment. We can develop operational procedures that minimize damage when storms arrive. These choices cost money and require sustained commitment, but they buy us options that we would not otherwise have. We can choose to invest in forecasting and monitoring. Every hour of additional warning time is an opportunity to protect equipment, prepare populations, and position resources for response. Better satellites, better models, and better communication networks all contribute to our ability to see storms coming and prepare for their arrival. We can choose to research and understand. Every new insight into solar physics helps us predict what the sun might do. Every historical record we decode, every tree ring we analyze, every ice core we drill extends our knowledge of what has happened before and what might happen again. Understanding the threat is the first step toward addressing it. We can choose to cooperate. Solar storms do not respect national boundaries. A CME aimed at Earth affects the entire sunlit hemisphere simultaneously. The response must be equally global. Sharing data, coordinating warnings, and cooperating on protective measures benefits everyone. Or we can choose to ignore the threat, to assume that what has not happened recently will not happen at all, to treat space weather as someone else's problem. This too is a choice, and it is the choice we have largely made for most of the past century. The May 2024 solar storm was a reminder that the sun has not forgotten us. The auroras that painted skies around the world were beautiful, but they were also a warning. The GPS disruptions that idled farm equipment during planting season were inconvenient, but they hinted at far worse possibilities. The storm was powerful by recent standards, but it was not exceptional by historical standards. It was not a Carrington event. It was not a Miyake event. It was merely a taste of what our star can do. The probability of a civilization-threatening solar event in any given year is small, but over decades and centuries, small probabilities accumulate. The Carrington event occurred 166 years ago. The Miyake events occurred approximately once per millennium. We cannot predict when the next extreme storm will strike. We can only know that eventually one will. The question we face is simple but profound. How much are we willing to invest to protect against a threat that may not materialize in our lifetimes, but almost certainly will materialize eventually? How do we balance the costs of preparation against the cost of catastrophe? How do we sustain attention and commitment to a problem that unfolds on timescales longer than political cycles and quarterly reports? These are questions without easy answers. They require us to think across generations, to accept costs now for benefits that may not arrive for decades or centuries. They require us to acknowledge uncertainty and plan for events we cannot predict with precision. They require us to take seriously a threat that has never affected most people alive today. The sun does not care whether we find these questions difficult. It does not care whether we find the answers. It simply continues its ancient rhythms, building and releasing magnetic energy, sending light and particles across 93 million miles of space to the small blue world that happens to orbit at just the right distance to sustain life. We are fortunate beyond measure. We live on a planet with a magnetic shield that deflects most solar radiation. We live under an atmosphere that absorbs the rest. We live during an era when our star is relatively stable, not prone to the superflares that some sun-like stars produce. We have won a cosmic lottery that allows us to exist at all. We would be wise not to squander that fortune. The dark spots on our sun are more than astronomical curiosities. They are warnings written in plasma and magnetism, reminders that the universe is not obligated to accommodate human convenience. They tell us that the same star that gives us life can also take away the systems we depend on. Who will pay the price of protecting our electric world? We will. Either we pay the smaller price now in investment and preparation and vigilance, or we pay the larger price later in destruction and recovery and lives lost. The sun is patient. It has been producing storms for billions of years and will continue for billions more. We are not patient. We plan in years and decades, not millennia. We discount the future and prioritize the present. We struggle to take seriously threats that seem distant and abstract. But the sun does not operate on our schedule. The next great storm will come when it comes, regardless of whether we are ready. And when it arrives, the beauty of the auroras will be cold comfort for a world gone dark.